Hello friends. In this video, we are going to study about the tri-state logic devices. The tri-state logic devices are very commonly used in the microprocessor circuits. So let's study about them. The tri-state logic devices, as the name suggests, these are ordinary logic devices, but these devices have three states, and these three states are logic 1, logic 0, and the high impedance state. As we see in the logic devices, that logic devices have logic 0 means the low level state, logic 1 means the high level state, and the high impedance state. This state is, because of this extra state, these devices are known as the tri-state logic devices. So logic 1 is the high level state and logic 0 is the low level state. So logic 1, suppose in any logic devices, it is giving an output of 0 volts. So 0 volt will be called the low level state, and the highest output given by the logic device, it is suppose plus 5 volts. So plus 5 volt is the high level state or the logic 1. So 0 volt will be the logic 0, and plus 5 volt because it is the highest voltage given by the or highest output given by the logic device, so it is the logic 1 state. Now as the tri-state logic devices, they are having an extra state which is known as the high impedance state. So in this high impedance state, the logic device, it behaves like as it is not connected in the circuit. Okay, so let's first study about the ordinary logic devices, that how they work, and then we will come to the tri-state logic devices. Now ordinary logic devices, they have two lines. One is the input line and the other is the output line. Okay, so on input line, the input to the logic device is given and the output of the logic device is at the output line. Now there is another third line which is called the enable line. So what's the use of this enable line? This enable line is used to on or off, or we can say connect or disconnect the logic device in the circuit. So when this enable line is high, or we can say that it is active, then the logic device will behave that like it is connected in the circuit. So whatever will be the operation of the logic device, like if we have connected the AND gate or OR gate, or we have connected buffers or inverters, then they behave normally when this enable line is active. Now when this enable line is inactive, the device will not work. So it will behave like as it is disconnected from the circuit, or we can say that when the enable line is inactive, the device goes into the high impedance state. So this functioning of the enable line, it is somewhat related to the high impedance state. So when this enable line is active, the device will normally work when like it's whatever was its function as an ordinary logic device, and when this enable line is inactive, the device will goes into the high impedance state. So we can say that when in the high impedance state, the logic device behave as if it is disconnected from the system. Now, in the logic 0 and logic 1 state, so in the logic 0 and logic 1 state, current is required to drive the system, whereas in the high impedance state, no current is drawn from the system. Let's take some example of the tri-state logic devices. This is a buffer. Okay, this buffer is having two lines. One is the input line and the other is the output line. Now, if we have a third line, which is called the enable line, then this buffer is called the tri-state buffer. Okay, now this enable line, in this case, it is active high. Means when the value at this enable line is 1, then the input is equal to the output. Means the input will goes to the output, because in case of buffer, the output varies according to the input. So if the input is 1, then output is also 1. If input is 0, then output is also 0 when this enable line is 1. If this enable line is 0, it means that this buffer will goes into the high impedance state, because this enable line is active high and we are giving 0 value at it. So this device will not work. Okay. And the second case is if we have the enable line as the active low. So here we have a bubble for it. So in this case, the active, this enable line is active low. So when the value at this line is 0, then the output will be equal to the input. It varies according to the input. So these are the examples of the tri-state buffer having active high enable line and active low enable line. Let's take another example of the tri-state logic devices. This is an inverter. So what does an inverter does? Whatever is the input, the output will be reverse of it. Like if the input is 1, then the output is 0. And if the input is 0, then the output will be 1. Now this is a normal logic device. Now if we have a tri-state inverter, then it will have the enable line also. And in this case, the enable line is active high. It means that when this enable line is 1, then we will get the corresponding output. Like if we draw the logic table, then this enable line is 1. Okay, when this is 1, then the reverse of the input we are getting as the output. Now if this enable line is 0, then whatever will be the input, the output will be, that is the device will be in the high impedance state. So this is how the tri-state logic devices they work. We have taken the example of the buffer and the inverter. Now What is the use of these tri-state logic devices in microprocessors? We know that the microprocessor, they perform communication or the transfer of data from the peripherals. Peripherals are the input output devices. So the microprocessor transfer of data takes place between the input output devices and the peripherals. Now these peripherals, they are connected in parallel between the address bus and the data bus. Okay, so these tri-state logic devices, they are connected between the input output devices and the address and the data bus, so that the transfer of data which is taking place, it does not load the buses. That is the burden on the buses to carry the 8-bit data or the 16-bit data, that is reduced due to these tri-state logic devices. Okay, so this is the use of the tri-state logic devices in the microprocessor. Now there are various types of tri-state logic devices which are used in the microprocessors, like buffers, encoders, decoders and latches. So here we are going to study about these logic devices. First we will start with the buffer. Now, what's the use of buffer or what's the function of it? Buffer is used to amplify the input. So, whatever the input is given, we get an amplified output. Okay. Buffer, it has one input and one output, and one enable line is there, as we have seen earlier. Like it is the symbol for the buffer. This is the input, this is output, and this is the enable line. This is active high, and if it is active low, then we have a bubble here. So these buffers, they are they act as a driver because they are amplifying the current or the power. That is, the input is amplified in the output. So as the buffer, it is used to increase the driving capability of a logic circuit. So it is also known as the driver. Now, if we see the truth table for it, we are taking the case when the enable line is active high. So when this enable line is 1, then only this device will work. So whatever will be the input, the output will be the same. If this enable line, which is supposed to be active high, if we are giving 0 input to it, means we are giving 0 at the enable line, then whatever will be the input, we are writing x here. X means that this value can either be 1 or it can be 0. It is irrelevant. Its value doesn't have any effect. So the output or the device will goes into the high impedance state. So we are saying that this is a tri-state buffer. This state, when the output is 1, this is the logic 1 state, or we can say the high level state. This 0 output It is the logic 0 state or the low level state, and the third state is the high impedance state. So due to these three types of state, this buffer is called the tri-state buffer. Now let's take example of some tri-state buffers. The first example is the octal buffer, whose IC number is 74LS244. This is the pin diagram for this octal buffer, and this buffer is also known as line driver or line receiver, and it is commonly used as a driver for the address bus. Now in the pin diagram, you can see that there are 8 buffers which are divided into 2 groups of 4 buffers, and each buffer is having 3 lines. One is the input line, one is the output line, and the third line is the enable line. Now the upper 4 buffers, they are having a common enable line, which is the 1G bar, and the lower 4 buffers, they are having a common enable line, which is called the 2G bar. Okay, now these 4 buffers will be activated when this 1G bar line, because here we are having a bubble and a bar over it, means this is an active low enable line. And this is 2G bar, so a bar and a bubble showing that this is also an active low enable line. It means that when this 1G bar line, it is 0, then these 4 buffers will be activated, means whatever will be the input, the output will be same, or we can say that the input data bit, it is transferred at the output. And if the 2G bar bit, this 2G bar line, it is 0, means it is activated, then the lower 4 buffers will be activated and the input data bit will be transferred to the output. So 4 bits can also be transferred, and simultaneously 8-bit data can also be transferred if all the 8 buffers are activated. If first upper 4 are activated, then 4-bit data will be transferred. If lower 4 are activated, then also 4-bit data will be transferred, and if all the 8 are activated, then 8-bit data will be transferred. So this buffer, this octal buffer, octal means 8, so 8 buffers are there in this IC 74LS244, and this is used as a driver for the address bus in the bus oriented system. So this is an example of a tri-state buffers which are connected in a single IC. Okay. Now the next example is that of a bi-directional buffer. Bi-directional buffer means it allows the data to be transferred in both the direction, that is from input to output and from output to input. That is in both the sides the data is being transferred. So this bi-directional buffer, it is used as a driver for the data bus, because we know that in the microprocessor the address bus, it is unidirectional and the data bus, it is bidirectional. So the data is transferred in both the directions. So this bidirectional buffer 74LS245, it can be used as a driver for the data bus, because data bus is bidirectional, and that octal buffer which we studied earlier 74LS244, it is used as a driver for the address bus because it was unidirectional. Now in this bi-directional buffer, that is 74LS245IC. We have, this is A1 to A8, that is 8 inputs we have and 8 outputs we have, and for each input output connection we have two buffers involved. So this circuitry, it is for all these 8 connections. Okay, we have just shown here for one. So for this connection we have two buffers, so for 8 we will require 16 buffers. So there we have 16 bus drivers, we can say, and 8 drivers are for each direction, that is from A to B we have 8 buffers, and for B to A, transfer of data from B to A, we have other 8 buffers. Okay, now the enable line, because each buffer is having 3 lines, input, output and enable line. So input line is there, output line is there, and enable line, it is provided by 2 lines. One is the DIR, direction control, and the other is the G bar. So these both are added, and then simultaneously they are the output line, it is given as the enable to this A to B buffer. Now for this B to A, another we have a combination of these two lines. Here you can see that we have bubbles for both the lines, and here we have bubble for only one line. Okay, so the direction of flow of data, it is controlled by the enable line. Whenever this buffer is enabled, then the data will flow from A to B. When this buffer is enabled, then the data will flow from B to A. Now the truth table for this bi-directional buffer 74LS245, we have the enable line, that is G bar, and the direction control line, this DIR is the direction control line. So when both these lines are low, then this buffer B2A, that is this buffer, will be activated and the data will flow from B to A. Now when this enable line is low and the direction control line is high, it means that this buffer will be activated. So the data will flow from A to B. This is written here. Now when this enable line G bar, it is high, it has to be low because we have bar over it, so it has to be active low. But if we are having a high input, that is 1 at this enable line, then the device will, or the IC will go into the high impedance state. This isolation means the high impedance state, and in the high impedance state the device work as if it is disconnected, means it is isolated from the circuit. Okay, so this is how the buffers, the tri-state buffers, they work. We have taken two examples, one for the octal buffer and second was of the bi-directional buffer. Okay, now the second type of tri-state logic device we will study is the decoder. So decoder are the logic devices which identifies each combination of the signals which are present at its input. So if we take an example, like if we have a decoder which is having two input lines. So these two input lines, if we give the binary data as an input 0 and 1, then these two digits on the two input lines, they can have four combinations like 0, 0, 0, 1, 1, 0 and 1, 1. Now these input lines, they will give us four output lines. 2 raised to the power 2, that is 4. So these two input lines can have combinations, 4 combinations. So we will have 4 output lines. So what basically the decoder is doing, it is identifying these each combination of the signals which are given at its input. We will give different output inputs, the two input lines, and for each of the input we have the corresponding output combination. So these two input lines, they are having 4 combinations. So if the input line one, then the third output line will be activated. If we draw the diagram for it, then we have, these are the two input lines and we have 4 output lines. So it will be a 2 to 4 decoder. Now suppose at the input we have 1 and 0, and these output lines we have 0, 1, 2, 3. So 1, 0 will be there, then the second output line, this 2 output line will be activated. When we have 1, 1, then the third output line will be activated. If we have 0, 0, then on this 0 line, this will be activated. Okay, so this decoder will be called the 2 to 4 decoder. Okay, so this is how the decoders work. Now, what's the use of decoders in microprocessor? Decoders are used in the interfacing the input output and the memory with the microprocessor. When we will study the interfacing of the peripherals and the memory with the microprocessor, then these decoders are used. And also the port select decoder, it is used to decode an address bus to identify the output device. So in the decoders, basically they are decoding the combination which is given to it as an input, and the corresponding output line will be activated. Now let's take an example of a decoder. We have 74LS138. This is a 3 to 8 decoder. So 3 input lines and 8 output lines are there. So we have 2 raised to the power 3 equals to 3 input lines can give us 8 combinations. So we have 8 output lines. Whenever the input, the corresponding input will give us that output line will be activated. Okay. So we have 3 input lines. So we have 3 input lines for this decoder, 8 active low output lines, that is the output line will be activated when 0 will be available at it, and we have 3 enable input lines, and out of these 3 enable input lines, 2 are active low and 1 is active high. So let's see the pin diagram for this decoder 74LS138, which is a 3 to 8 decoder. So this decoder, this is the pin diagram for it. It is having three input lines A, B and C, which are connected at the pins 1, 2 and 3. And we have the 8 output lines from Y0 to Y7, and these 8 output lines are connected at these pins. Then we have at 8 number pin we have the ground. Then at 16 we have the VCC, that is the power supply. And at 4, 5 and 6 we have the 3 enable input lines. So you can see that in these enable input lines, one is active high and the other two are active low. So this device will be activated or it will be enabled if the G2A bar and G2B bar, these two active low enable lines, they are 0, and the G1 enable line, it is 1. Okay, we have the bubbles here to denote that these are the active low enable lines, and this is the active high enable line. These are connected at the pin numbers 4, 5 and 6. So this is the pin diagram for the 328 decoder, which IC number is 74LS138. Now let's see the truth table for it. Now in this truth table we have two sections. One is for the input and the other is for the output. In the inputs we have the 3 input lines A, B and C, and also the enable lines G1 and G2. Now one enable line is G2B bar and the other is G2A bar. So A and B are the input lines. Okay. So G2 and A and G2 and B, they will form these two enable lines, G2A bar and G2B bar. Now this this G2A bar and G2B bar, they have to be 0, and G1 line, it has to be high for the device to be activated. Now if this G2 is high, then if any of the input we are providing, the output will always be high. As this decoder, 328 decoder, it is having the active high output lines, active low output lines. It means that if when we are having 0 at any of these input lines, then it means it is activated. Otherwise they will always give us active high output, that is 1. Okay, so they are all having the active high output. If this G2 is high, and whatever will be the value of G1, that means either it can be low or it can be high, it will have no effect. If this is high, then the output will be high always. Now if this G1 is low, then also the output will be high. Okay, because we know that this device will be activated only when G2 is low and G1 is high. Okay, so here we are giving the combinations. Now we will take each of the combinations of the 3 input lines A, B, C. First we are taking low, low and low. It means we are giving 0, 0 and 0. So 0, 0, 0 is the input. So the output line Y0 will be activated, means it will be low. If we are having 0, 0, 1, that is low, low and high, then first output line will be activated. It means its value will be low. Similarly, if we are giving like high, high and high as an input, that is 1, 1 and 1, then the last output line Y7 will be activated. It will give us the low output. Because here we are having the bubble signs, it means they are active when we are getting 0 as an output. So what this decoder is basically doing, whatever combination or whatever code you are giving at an input, it is decoding it. That is, if you are giving the code 000, it means that this code is for the output line Y0 and it has to be activated. So it is decoding that code which is given at the input. So this is the working of a decoder, how it decodes the code which are given, or the combination of inputs, and then give us the corresponding output. Now the next type of logic device which we are going to study, it is the encoder. So encoder, it is a logic circuit which provides the appropriate code as output for each input signal. So whatever input signal you are giving, it will generate a code for that input, or we can say that it is reverse of decoding. So in case of decoder, we were having 3 to 8 decoder. Here we will have 8 to 3 encoder. So this encoder, it will have 8 input lines and 3 output lines, and for the combination of each combination of the 8 input lines, there will be a particular code. So this is 8 to 3 encoder, which is having 8 input lines which are active low, and 3 output lines which are also active low. So if we are having, suppose there is a combination here, so that corresponding output line will be activated. That means its value will be 0. So here we have the A2, A1 and A0. These are the output lines. A2 is the most significant bit and A0 is the lowest significant bit. That is, in this way we are going to study starting from the MSB to the LSB. Okay. Now what the encoders uses there in the microprocessor. So the encoder, if we are giving 2 or more input lines we are activating at the same time, then the encoder is unable to provide us an appropriate code, because it gets confused that which line or which output code it is providing. Suppose that in the encoder, suppose the 7th and the 5th input line both are activated, then the encoder get confused that which output code it has to provide, either for the 7th or for the 5th line. So for this problem solving, we are having the priority encoders. So these encoders, they check that which of the line it is having the highest priority. So the line which is having highest priority, it will generate the code for that. So the priority encoders, they can solve the problem of simultaneous input. Let's take an example of it. We have the 74LS148 priority encoder. Let's see the pin diagram for it. This is the pin diagram for the priority encoder 74LS148. This is an 823 priority encoder. It is having 8 input lines and 3 output lines. You can see that the input lines, these are active low, and the output lines, they are also active low. Here we have the enable line, that is E1, and E0 and GS. These are the additional lines which are connected at the pins 15 and 14. Now let's see the truth table for it, that how the priority is being decided. We have the sections for input and the output. We have the 8 inputs, 3 outputs, and also we have GS and E0. Then this enable line, because it is active low, so when this is low, then only the encoder will work, otherwise it will goes into the high impedance state. Now when this is low and we are giving the input as high, high and high, all are high here, so the output will also be high, because we are having active low inputs. The input lines are active low, so if we are giving the input as high, then output will also be high, and the GS and E0 line, they are high and low. Then if we are giving like this is having no effect, if we are having the 7th line is at the low, that is active low, and this GS line is L and this is H, okay, that means GS is low and E0 line is high, then the code for this 7th input line will be generated and it will be 0, 0 and 0, okay. Then if we have this 6th number of input line, it is low, then we have the output code for it 0, 0 and 1, and you can see that this GS and E0, in all the cases E0 is high and GS is low. So in this way the priority is being decided, that for this by these lines GS and E0, and this is how the priority encoder it works. So encoder is just doing reverse of the decoding. In the decoders we have to decode the code for each of the input, and in the encoders we will provide the code for each of the inputs. Now the last tri-state logic device which we are going to study, it is the latch. Latch is also known as a D flip-flop, that is D flip-flop is the other name for the latch, and it is also known as transparent latch. Now latch is used to hold the data until the next clock cycle, okay, and this latch is having a very important use in the microprocessor. We know that in the microprocessor the lower order address, it is available only for the 1T state, and the higher order address, it is available for the 3T stage. So for the lower order address to be available for a longer period of time to the microprocessor, latch is used. So latch, what it basically does, it holds the data until the next clock cycle. We have an example for it. The 7475D flip-flop. This flip-flop also acts as a latch, and the IC number is 7475. So in this latch, when the enable signal is high, then the output changes according to the input. That is, it is having a active high enable line, and when this enable line is high, it means the device is activated, and the output will change according to the input. That is, whatever is the input, the output will be same. So let's see the output of this 7475D flip-flop. This is the diagram for it. We have the 7475, the latch. It is having the input at the D, and we have a clock here. Then we have the output Q. Now this is the clock cycle, which is showing all the connections here. In the clock, we have the first time period, that is from T1 to T2. We have T1 to, then T2 to T3. This time period is T2 3, and from T3 to T4 we have T3 4. Now this is the input which we are giving to the latch. Now this latch is a level triggered latch. That is, whenever the clock cycle changes from low to high, that is, whenever the level of the clock cycle is changing, the input or the output will change according to the input. Here the level is changing at this T1, so this input is, the output is same as that of the input, and when this clock cycle is low, then this output, just before this, what is the output? It is high, so this high output will be carried on till the next clock pulse is given. So this next clock pulse is given at T3. Now at T3 the input is high, so again this is high, then it comes to low, then it comes to low. Now the level is changing here, the clock pulse is ending, we have negative part of the clock cycle, so this input is low at before this period, that is T4, so this low output will be latched until the next clock pulse is given. So whenever the clock pulse is given, the output will change according to the input, and when clock pulse is not given, then that output will be latched until the next clock pulse. So this is the case of the level triggered latches. Now take another example of the 7474 latch. This is a positive edge triggered latch. So in this case, whenever the positive edge is given, that is from low to high, here also from low to high. So whenever the positive edge is given, then the output will change according to the input, or the input will be latched for that clock pulse. Now this, at this positive edge, the input is low, so low input will be taken till the next positive edge is given. Now next positive edge is at T3. Now at this position the input is high, so high input will be latched till the next positive edge. So this is the difference between the level triggered latch and the positive edge triggered latches. Latches are also tri-state logic devices. They also have the enable lines in them. It depends that whether it is active high or active low enable lines. So in this video, we studied about the tri-state logic devices, which are very commonly used in the microprocessor circuits whenever the peripherals and the memory is communicating with the microprocessor, so as to lower the burden of the buses. So I hope that this video is clear to you and this topic is understandable to you. Thank you.